Hello. Today I want to focus a little bit more on the idea of electrical resistance and the factors that affect the resistance of an object, the electrical resistance of an object. So there's four main things that affect the electrical resistance of an object. One is what it's made of. Okay, that's obviously an important one. Something like a copper wire would have typically, or the material copper has a very low resistivity. Okay, whereas something like a glass, it has a very high resistance. Okay, so copper would have a low resistance and glass has a high resistance. Two, okay, another thing that affects the resistance of an object is the length of it. Okay, which will tend to be have a higher resistance, a short object or a tall object or a long object. Okay. Well, the one that will tend to be more resistive, okay, is the long object. So the length. The longer the material, the more resistance it has. Okay, which will tend to be have a greater resistance here. Okay, the thick wire, okay, or the skinny wire, which would be harder to push electrons through. Okay, which would be harder for the electrons to flow through. A wide highway or a skinny road. Okay, it's going to be harder to get through the skinny road. So the thin wire tends to have a greater resistance. Okay, and four, the electrical temperature. Okay, the temperature. Okay, the hotter an object is, the more resistive it is. Okay, the higher its resistance. And in extreme cases, you've heard of superconductors. Whereas if for certain materials, if you cool them down enough, they don't have any electrical resistance whatsoever, and they're considered superconductors. Okay, so warm things tend to have higher resistance than cool things. Okay, what would happen to the electrical resistance of a thick, short wire if I stretched it out into a long, skinny wire? Okay, what's going to happen to the electrical resistance? Well, let's look at two parts. Okay, one, it's going from a thick wire to a skinny wire. What's that going to do to the resistance? Okay. Well, skinny has a higher resistance than thick, so that's going to cause it to increase in resistance. Okay, let's look at the other thing. That's the short to a long. Okay, what's going to happen when we go from short to long? What's that going to do to the resistance? Well, that's also going to increase the resistance. So for twofold factor, the resistance is going to increase if you stretch a wire out. Okay, so this is a magnified 100 times magnification of the light bulb filament of the old school light bulbs, the one where the filament can burn out. And what's interesting is when you look at that, it's not just a filament, it's not just a wire that stretches across from that, it's a twisted wire, and they twist it into this spiral, okay, and then I think they even spiral the spiral. Okay, so that skinny little filament that doesn't look that long is actually a whole lot longer than it looks like because of the way they spiral it. Okay. You may have seen these, something that looks like this if you've ever opened up a device that's got electrical components. These are specifically called resistors, and they have a colored band system to tell you what resistance they are. Each color stands for a different amount of resistance. So that's what these bands are on them, if you've ever wanted to know, and they come in different sizes as well. Okay, this is the symbol or the equation for the resistance of an object. So there's and this takes into account all of our factors, okay, except for one. Okay, so this row, this little P-looking shape here is a Greek R, okay, and it's the resistivity of a material. Okay, this is where we take into account the material itself, and there's tables and tables of materials and the resistivity. So resistivity, okay, not resistance, but resistivity. This is where we take into account the length, okay, the length of the object, typically a wire, okay. And A is the cross-sectional area of the wire. So if you're given the radius of the wire or the diameter, okay, find the radius and do pi r squared, okay. So this is a table of different resistivities. So we see these appear to be going from low resistivity to high resistivity. Silver has a very low resistivity, 1.59 times 10 to the minus eighth, okay, which is a better conductor than copper. Copper's got a little bit of a higher resistivity, but not by a ton. Why is copper used instead of silver? Well, copper is a lot cheaper, although copper is pretty expensive now too. Aluminum has an even higher resistivity, but it's used for wires, or was used for wires. I'm not sure what time frame. Okay, and then we start getting into the insulators, like glass, which goes from 10 to the minus eighth from silver to 10 to the positive ninth, so an order of magnitude of 10 to the 17th difference. And hard rubber, which is used as an electrical insulator, 10 to the 13th. So this is where we take into account the material itself, and the units of resistivity are ohm meters. Okay, so let's work a problem here. What is the electrical resistance of 25 meters of 12 gauge copper wire, which has a radius of 0.00102 meters? Okay. So this is pretty much plug and chug. So find the table, we'll find copper. So the resistivity of copper is 1.68 times 10 to the minus eighth. Okay. Again, 1.68 times 10 to the minus eighth. Okay, times the length, which is 25, and divided by pi times the radius squared. Okay. If it didn't give you the radius, you probably had to look up the radius of 12 gauge copper wire. Gauge is how the thickness of copper wire, or a lot of different things, the diameter is measured, is referred to as gauge. Okay, if you've ever heard of a 12 gauge shotgun, that refers to the diameter of the opening. So you punch the numbers, you get 0.128 ohms, okay? Or I could have used that horseshoe symbol here instead. So not a whole lot of resistance, but real wires do have an actual resistance. It's just, for the most part, can be negligible, okay? How would the resistance be? Oh, we already looked at that one. Okay. The one that we left out, and we're not going to worry about it, is temperature. Okay, and where you take into account temperature is this coefficient of temperature, which is right here, this temperature coefficient. And so there's a conversion equation that basically you look at how far the temperature is from probably to 98 Kelvin, and then you take into account using this equation. So, like I said, we're not gonna worry about it. Okay. What causes the resistance of the electrons moving through a conductor? What happens to their energy as they move through the wire or a resistor? Let's see if this applet will pull up. Usually it does not take this long to load up. I hope these don't start taking this long to load up. So this is a battery resistor circuit. So here, this shows a lot of different things. So so this represents the protons or electrons, depending on what system you're going by here. Let's call them electrons. And here they're smacking into the electrons and the atoms in the wire. This represents the resistor, I guess. They're smacking into the atoms or the electrons of the resistor. Okay, this represents a pinwheel, which is reducing the voltage and removing energy from our system. So, what's going to happen to the current of our system as I increase the voltage? So, if I increase the voltage, what's going to happen to my flow rate of electrons or protons? Okay, oh, wrong way. Well, you can see that my flow rate increases. Okay, the electrons start moving faster. Okay, or protons. Okay, if I reduce the voltage, they start moving slower and slower and slower and slower. Okay. Um, Now, what happens on the inside? Notice that the atoms start bouncing around faster and faster. That represents that the atoms inside the resistor get hot. Okay, and how do they get hot? Well, the electrons are smacking into them. They're being accelerated across this due to an electric a an electric field. Okay, an electric field is accelerating the electrons across it, and they're smacking into the atoms, causing it to get hot. Now I know I showed you what was inside a battery, but these are special batteries. If you look inside this battery, there's little ferries that carry the electrons from one end of the battery to the other. So in case you ever want to know what's inside the value batteries or whatever, while they run out, the ferries get tired. Okay. Um, um, I think that's about all I wanted to show here. What happens if I increase the resistance? What's going to happen to the flow rate if I increase the resistance? When I increase the voltage, the flow rate, the current increased. When I increase the resistance, what's going to happen? Okay. Well, when I increase the resistance, the electron flow rate decreased. Okay. When I decrease the resistance, the flow rate increases. Okay, as shown by my little paddle wheel. That's my voltmeter. Okay. All right. Um, all right. So if you have a piece of copper wire, okay, but it's not connected to a battery, are there any electrons in it, or is it empty of electrons? Of course, it's got electrons in it. Okay. Um, in a neutral wire, the electrons in a neutral conductor, the electrons are able to move around. Okay. And they do so randomly. They don't really end up going anywhere. It's called the drift speed of the electrons, and they just kind of bounce around and don't really end up going anywhere in particular. Um, oh, but when you apply an electric field, okay, they're still bouncing around. They still bounce around due to especially due to the temperature. I misspoke. The net migration of the electron in the electric field is known as the drift speed. Okay, so this is the path, the more realistic path of an electron. It's probably a lot more zigzaggy than this, but when you apply that electric field, you get the drift speed. Okay, the drift speed in a wire is around 1 millimeter per second. Okay, the actual electron speed is around 1.5 million meters per second. So the electrons are really, really cruising around in a conductor, at least at room temperature. But the drift speed is much, much slower than that. So the electrons don't move that quickly in terms of around the circuit. Okay. And if you flip a light switch, okay, you figure there's about, I don't know, a couple meters of wire between the light switch and the light. Okay, at 1 millimeter per second, that's a long time for the electron to get from your light switch to the light bulb. That's a long time. Okay, why doesn't it take hours for your light switch to turn on? Okay, or your light to turn on? Okay. Well, the reason it doesn't take that long is the wire is already full of electrons. So when you pump one electron into the wire, one electron goes out of the wire, okay, quote unquote out. It goes through your light. Okay, so as electrons are flowing into the light switch at 1 millimeter per second, they're also going to be flowing to your light at 1 millimeter per second. Okay, all right. Um, so as these electrons are moving around like this, they're constantly bouncing around and bumping into things. Um, they smack into the atoms and electrons in the resistor, okay, just like the animation showed, and that's what causes the wire to get hot, is the electrons bumping into the atoms and that kind of thing. Okay. Um, so the reason that the resistivity of a resistance of a wire goes up as temperature goes up is the hotter the wire is, the faster the electrons are moving, and the more rapidly they're bumping into the atoms. Okay, and in doing so, they're getting slowed down more and more, um, or they're getting more resistance. Okay. Um, Okay, and that's it for today. So if you have any questions, please email me. Good luck on your studies.